Hi everyone, welcome to this week's DevCuts. This is a follow-up to last week's episode where we did a brief rundown on features of the new BSP for our iMX8MP lineup. And this one is going to be a little more developer focused, and we're really going to focus on the bits that have been added and how to make the most if you're using the Basler Camera system, especially with the neural networking inferencing and just some things that I found that allow you to get the best performance out of the board when you're trying to do vision processing. I'm not going to go in depth into building neural networks or anything like that. All I'm really going to focus on is the processing of the video in order to keep the pipeline, to get the most out of the product and get the pipeline moving as fast as possible. But first, I'm going to briefly just go over a few things with how the NXP's iMX ISP is integrated, and just some things you might be interested in if you want to do simple things like flip your video around and have it be hardware accelerated, those sorts of things. So let's dive in, and I'll show you a few tips and tricks. So here's our iMX8MP running the latest BSP. And let's just choose the simplest thing. Well, the first thing you want to know is there's many stages to the vision processing that's going on the iMX8MP because it has its own ISP, it's got its own dewarping engine, and all sorts of high-end camera features. We'll talk about that a little bit more. For now, I just want to show you the basic directory structure, where everything is, and the daemons that are involved, those sorts of things. So if we go into opt iMX8-ISP on our BSP, and then into bin, you'll see here we have start ISP, run.sh, and then a whole bunch of configuration files, and then a few directories like dewarp config. And you'll see there are different variations of this depending on the sensor you're using. Most of this is detected on startup, and it is running, if we look at that, see here we have our iMX ISP bin run.sh, and by default it's running the dual Basler camera in 1080p 60 on our ISP. Just because with vision processing, 1080p is generally more than you're going to need for an image. Most of them are just doing 720, but thanks to some optimizations I'm going to show you, I have been able to do 1080p 30 frames per second around that with inferencing involved. But as far as the camera is concerned, most of the Basler BSP is already integrated in here, so there's not much you have to do. Just a couple of things that are handy for me that I've used is by default, if you want to flip the camera around and have it upside down so you can run your cables differently, you can do this in a hardware accelerated manner. You just head into the dewarp config, and this file does a lot more things. I'm not going to go into full in-depth for that. I'll show you where you can find more information, and especially if you want to tune your own sensor or use some of the advanced features. NXP has great documentation on that, so I'm not going to double up and re-explain it. But I did have to track this down, so I'm going to share it with you. Here we have the DA 3840, that's the BSP. And then the 30MC is the lens at 1080p. So this is the fisheye wide angle lens. Well, it's not a full fisheye, but it's a wide angle lens, and it is set up so it's doing lens correction. And down here you can see that's where the distortion coefficient and the camera matrix and perspective come into play. All this needs to be calibrated, and again, NXP has that all documented. But just the quick things that you might care about. Bypass means it'll still bring up the camera, but it'll bypass running through the dewarp configuration, which fixes the angles and squares them away. But what is useful is if you have if you want to mount the camera differently in whatever system you're using to show your demo off, you can just switch these just flip the camera in both directions. So if you want to have the camera upside down from its normal orientation, you can change both of these to true. And then you need to restart iMX ISP system D service. And then if you then want to launch your camera up, and we can switch over, and there you can see I'm upside down and backwards. It's a simple thing, it's not big. It did take some poking around to find, and so I figured you would I could share that with you, especially if you have a specific mounting format you want. I'll just switch that back for the means of this demo and restart it, and then we can see, and then I'm back right side up. And really, and so those are the bits you really need to know. It's the iMX ISP System D service, which is starting the cameras and linking them. If I do run on this specific system, even though this is our Hummingbird Mate, so this does not have the dual sensor capability because there isn't a MIPI CSI connector on the board. However, I'm running it directly off the SOM, and so we will only have one camera device, but you'll see that there's a few sub devices, and this service is linking them all together and setting up the pipeline so you can take full advantage of their camera system. Again, I'm not going to go over this. NXP's documentation is great. Here's their website. Switch over to it. If we scroll down, we can see here we have they talk about the ISP, porting camera sensors, ways to configure the ISP. All of this is well documented, and since we're based on NXP's BSP, all of this is relevant to our board as well. If you have any questions, you can bring them up in our community forums. Normal means to get to talk with us. While I'm here talking about their documentation, I will also point out for in-depth information about their neural network BSP and its configuration, they have their i.MX machine learning guide. That's also freely available online. They talk about TensorFlow Lite, RMNN, ONX runtime, and basically all the bits and pieces of their neural network BSP and integrating it. One of the things I found when I was working with that was you can get decent performance, but I was seeing bottlenecks just using simple Python and OpenCV. If you're using the NN inference and the GStreamer pipeline, that's all integrated great. However, I know a lot of people would want to customize it or run a lot of the examples that are online, and those are all based around OpenCV and running your TF Lite model through there. And so I kind of delved into what was available, not just our platform, but things that have been done with the Raspberry Pi and the Coral neural network accelerator, and things that are available for Jetson and NVIDIA. And so I hacked together a script that's available as a gist, and I'll be linking to that in our community forums post about this, as well as I'll link to all the documentation so you don't have to go Google searching for that. And there we have, and here's my gist. I'm just going to cover a few things that I found that basically really brought up the frame rate. When I first took the script, and if you go down to the very bottom of it, you'll see this is the very standard OpenCV, grab a video frame, parse it, run the inferencing on it, draw the boxes, that sort of thing. This is for MobileNet and object detection. But I was finding that the performance was really lacking, and so what I decided to do was kind of to look directly into it. The first piece that I found was, most of the demos just pass the OpenCV video getter, the device to use or the file, and then let it do its thing and parse it and get the frame out. And we're using GStreamer as a backend because that has the full support for all the acceleration of the video decoding and the ISP and all those bits. And I found that was the first bottleneck. So the first thing I did, and again, this is variations of existing projects and code that are out here. I just hacked this together. Some of it's mine, some of it's other people. It's all semi-licensed or on StackFlow. But this is more of an example of what you can do. And so the first thing I did is to create this video getter class. And the reason for that, the main reason for that, is being able to break that off into its own thread. So now we have the main thread, which is doing the inferencing, either on the CPU or accelerated, and it's drawing the boxes and the output, but we've moved our video capture pipeline to its own thread. And that improved things quite a bit, but then there was I was still seeing our GStreamer pipelines were kind of limiting our frame rate. With this change, I got up from originally just everything being sequential. We were doing 10 frames, right around there. And then once we moved to a new thread for this, we were moving around 14 frames. Of course, I wanted to get as real time as possible. And so when I looked at the pipeline and I broke it up so we could do our own, here I'm using, the first thing we're doing is decoding, which will, if it's supported, we'll use the VPU to decode the video. But then what I'm doing is I'm using the graphics card 2D engine in order to do the resizing and the format conversion down to whatever we want our output to be. So if we have a 1080p video or a smaller video and we want to show it at a different resolution, we're doing that first large conversion using the 2D engine of the GPU, the Vivante G2D engine. But one of the problems with that is it only supports BGRX. It has the alpha channel, which is always there. And OpenCV wants RGB, BGR, that's it. So where we could resize this to whatever we wanted, we would still need to run it through a CPU-based video convert. And that was then a problem. I mean, they are 1.8 gigahertz, but they're Cortex A53 cores. And in recent BSPs, the support's been added, and you can use this nthreads property to video convert, and that allows more threads, more of the cores to be used to be doing the video conversion, which is great. It's just what we wanted. I have it set to 3, just because we have the main thread, we have the thread that's being used for the video decoding itself and running the hardware acceleration. And so I just balanced it out and made this 3 for any overflow. And there you see where we convert this to BGR. That's the only thing we're doing with this specific conversion. And so that allows this frame to be ready to be passed into OpenCV. Now, in our get loop, we also have this process frame, and what we're doing there is that's where we have to resize the frame to get it ready to be passed into the neural inferencing engine. And that's where we take it. If the frame's available, we convert it to RGB, which is what the TensorFlow Lite wants, and then we resize it down to the size that's been asked by the TensorFlow model. And then we pass that back. So we're going through a couple of color conversions or format conversions and a couple of resizings, and we're trying to utilize as much of the device as possible in order to make that a real-time thing. And it works a lot. With this, I was able to start processing up to 1080p right around 30 frames per second. It'll dip up and down a little bit for the inferencing, but for me that was good. Most of the other demos I've seen are only showing 720p 30, so this is a big jump in performance as far as I'm concerned. The other things, if you're using OpenCV, that you'll want to know about is using the engine itself. By default, if you just run this code like you get it off the off StackFlow or somewhere, you're just going to be using the CPU. And the pieces that are of interest to you are you need to load a delegate for the TF Lite runtime interpreter, and then further down you'll see here where I pass it experimental delegates, and I load the delegate libvx delegate. So this is the code that's hooked into the BSP, which is abstracts the neural network inferencing engine, and so it allows it to be hardware accelerated. So with those things out of the way, the one other bit that really tops things off is every time if the engine and everything has to build the graph, that can be a little slow. And again, this is all in NXP's documentation. I'm just bringing it out and kind of talking about it and showing you some pointers. So if you're trying to make your model run faster or restart faster, these are things that you'll want to do. And that's these two bits right here. And these are just two environment variables. The first one says to cache the binary, that graph that's generated, and then the second one's where to store it. So I stored in /temp, so if I'm just running the model over and over, tweaking things, it comes up nice and quickly. And then, but if I restart, it's going to generate it from scratch. And that basically covers all the optimizations I've done. I know I'm going through this quickly, but I will link to this and then if you want to use it, tweak it. It's not pretty. It is hacked together, but it's effective, and it'll give you some pointers if you're just trying to get a little bit more performance on our board. With that being said, why don't we see how it does? So here I am back on the board, and I have my this is the object detection model. In models, I have a couple of one. What I'm going to be using today is just the default one from TensorFlow Lite's object detection. You can just download it and run it. Again, this is not optimized in any way from a neural networking. It's not trained in anything specific. This is just the generic model. I downloaded, I extracted the labels, and I'm passing it video. And let's see how it does. So we will start. We're just going to take the camera and we'll run it at 1920 by 1080 and see what it does. So here we go. Now you'll see this is going to be slower. This is where this is a fresh reboot, so we don't have the model cached. And there you go. Oh, and so now it's come up. And let me switch over, and here you can see we're doing pretty good. We're getting right around 30 frames per second, which is, for 1080p, is not bad at all. And then if we switch back quickly, I will now just show you how much faster it comes up on the second run, since we have cached that grasp. And there, in that amount of time. So, you know, we're talking seconds of warm up rather than a lot. And this is running great. Like I said, this is just an untrained model, and it's on a green screen, but you can see it'll detect my cell phone. I think the model can detect scissors or cell phone. There. Again, it's not ideal. It is what it is. Out of the box, it's doing a good job. It's parsing it really quickly. If you just want an idea of what kind of performance we get, we can change this to do 720p in a window. I will talk about the commands in just a second. And so then if we switch over to a window, you know, there we see the frames are much higher, but well above the 30 frames per second. And these are inferencing frames. I don't have it locked to VSync or anything like that. So that's the normal demo, and it can detect chairs and TVs and those sorts of things. But let's see how we can make it useful. And this was kind of the goal when I was shooting, trying to optimize it. Was one of the things that can be run is is it can detect traffic things, and so I wanted to see if we could make that work. And that's here, we'll make that full screen. Just a quick rundown of what we're doing with the script. This is a script that suggests the model dir is where our models are stored, and I'm using MobileNet, passing it the label file, and then the resolution tells it what to convert it to, what you want to output it as. Full screen is self-explanatory. And then OpenVX tells it to run it with the neural networking engine. So now let's fire this up and see where we get, and I'll switch you over here, and here we are running. This is a 1080p 30 video of it's a free traffic video that's been pulled down, and this is running on the machine right now. Let me check. This is using under 4 watts to do this processing. Of course, this could be through the camera as well, and this isn't perfect. Like I said, it's not trained. This is just off the shelf, but you can see it's picking up everything going on in this busy intersection, and keeping a nice frame rate of, inferencing it above 30 frames per second. So it's pretty impressive. I think most of the demos I've seen have only been around 720p 30. So you can see how just simple tweaks on the processing itself, the information before you pass it to the neural network engine, can really unlock the potential of this system on a chip. And if we wanted to, we could also do it. We can do this in a window, and that should be good. And there you can see we can get even more frames per second. We're up in the 50s and 60s, so it's quite adequate. And just in case you were wondering, one more time, I will just run this without the neural network engine, and we can see what we get with the CPU. and there we're getting like 4.6 inferencing on. It's much different, and so obviously you can see the benefits of having that neural network accelerator on the board. And so that basically covers everything that I wanted to go over. We're excited to have this product. We actually think the BSP's gone a long way. NXP's doing a great job. They have great documentation. And then anything we've done beyond that, we can fill you in on, and we'll keep making more cuts for you. I hope this helped you out. You can check out our community forum. The link will be down below, where I'll have all the links to the documentations, the gist, everything, so you can get up and running as quick as possible. Okay? Have a good day.